Welcome to another talk of the dynamical systems in triangulated categories and surfaces. So today we have Fabian from University of Oxford, which will be telling us about Serre dimensions of triangulated categories. Take away, Fabian.
Thanks, Ed, for inviting me, and thanks for putting this all together. It's really great. And so what I want to talk about is kind of how you one can maybe define dimension. So this is a question that I find sort of fascinating personally. What is the dimension of a triangulated category? It seems like such an abstract thing. It's not something that you can easily draw a picture of, but what does a triangulated category look like? But, so it's kind of a bit mysterious thing. So what is its dimension? And here, really dynamics sort of enters and can be used to as an approach, sort of an application of dynamics. So yes, so the sort of basic question is there some kind of good notion of a dimension of a triangulated category? And this is very vague question. So first of all, what kind of number should it even be? Should it be a positive integer, or can it be negative? Can it be a rational number? Can it be a real number, or even complex number? Or even, there's not a unique number, but it's really better to see it as some kind of spectrum or set of numbers. Then the question is, is there really a unique notion of dimension, or are there several ones which have all their place and sort of usefulness, right? Which is kind of actually what happens, I guess, already in commutative algebra. Several, or homological algebra, there's different notions of dimension. And then the question is that, probably it's too much to hope that for any triangulated category whatsoever we'll have a good dimension theory, but we need to restrict to some kind of nicer behaving class of triangulated categories, maybe enhanced. So I think sort of the minimum actually, so it should sort of, at least you should, if you'd give me a notion of dimension, at least it should be defined for smooth and compact DG categories, so enhanced, which I'll remind you again what that means over a field. Okay, and by the way, interrupt me at any point if you have questions or some comments. Okay, and probably Calabi-Yau categories appeared, but I'll just remind you. So there's a kind of class of triangulated categories where there's a sort of, by definition, they have a dimension, which are the Calabi-Yau ones. And so, I mean, here there might be also other notions of dimension which might not exactly agree with this Calabi-Yau dimension, but I think this is sort of the most obvious dimension we would assign to it. And basic idea is, so if we have a compact manifold X, just sort of an analogy of dimension D, then we can actually read off its dimension from the cohomology or homology, because it will satisfy Poincare duality. Right? So whatever, it will be some top non-zero cohomology group, and that will tell us the dimension if it's a compact manifold. And so what's the definition of a Calabi-Yau category? And this is sort of the most basic one. There's more advanced ones. So a triangulated category, here I want it to be defined over some field. Right, in general, the Hom just needs to be an abelian group, but here this means that Hom is a vector space over some field, and it should be sort of the total Hom, meaning in all the various degrees, so the sum of the dimension of the X groups should be finite. I think it's sometimes called locally proper, or maybe X finite, which is standard condition. So if we have that, then the category is Calabi-Yau of dimension D if it satisfies this sort of duality, which is, looks like Poincare duality. So X D minus I is between two objects XY is the dual to XI in the other direction, so from Y to X. or you could say that it should be some, and this isomorphism should be actually, so it doesn't really matter right now, but usually it should be functorial in X and Y. Yes, so that's Calabi-Yau of dimension D, and I mean, there's some kind of pathological. If the category just consists of the zero object, then maybe D is not well defined. But in non-trivial examples, D, it can be Calabi-Yau some dimension and some other dimension simultaneously, like for manifolds. Okay, so these are Calabi-Yau categories, and this fits very well also with sort of geometric notions of dimension. So, and if the triangulated category comes from geometry, then this Calabi-Yau dimension really is sort of the dimension of the original space. So, say X is a smooth projective variety over some field of dimension D, and it's also Calabi-Yau. This has several definitions, but yeah, here we just want that. We just need that the canonical sheaf is trivial. It's a trivial sheaf, structure sheaf. And then Serre duality implies that the bounded derived category of coherent sheaves on X is D Calabi-Yau. And so that's kind of where the name comes from, Calabi-Yau category. On the other side of homological mirror symmetry, in a way, if you have a compact symplectic manifold of real dimension 2D, then its Fukaya category is D Calabi-Yau. Yeah. So if you don't know what Fukaya category is, you can just ignore that. But if you're familiar with it, it's some kind of category in symplectic topology where the objects are, roughly speaking, Lagrangian submanifolds. So they are D-dimensional things. And the reason why it's Calabi-Yau, basically, then it comes back to Poincare duality for this submanifolds, for these half-dimensional submanifolds. Yeah, and that is just a comment that they're often, so these actually satisfy kind of stronger things. So the stronger versions of this Calabi-Yau property, which have to do with cyclic cohomology or the cyclic complex, but it will not be relevant here. And then they also depend on having a DG enhancement of your category. So your triangulated category, right? So this definition really works for triangulated categories. It doesn't really matter if it has a DG enhancement or not. But sort of more sophisticated definition than you want to be in this DG setting. Okay, but this will be enough for now to define the dimension. But most categories are sort of not Calabi-Yau still, but they still have some notion of duality, which is what Serre functors are about. So what's the Serre functor? And this, of course, generalizes Serre duality for objective varieties. So let's say we have some triangulated category over a field. And again, it has this X finiteness. So sum of dimension of X I between any two objects is less than infinity, right? And Xi is just my notation for Hom. On the other slide. So this means Hom X I from X to Y is just Hom in the triangulated category from X to Y shifted by I by definition. Yes, so let's assume we have a triangulated category satisfying this condition. And what is a Serre functor? It's an order equivalence of the category, so that it kind of, you have natural, again, a sort of duality like this. So that the group from the X group from X to Y, like I said, some, sorry, needs to be other way around here. It's the advantage of handwritten slides that I can correct them in real time. think this is hopefully that should be the right way. Yeah, it doesn't matter, but one of them just needs to be switched. So the point is that the x from x to the Serre functor applied to y should be related to x, or kind of dual to x from y to x. And there's a minus sign. So it generalizes the previous definition of Calabi-Yau category, where in the Calabi-Yau case, the Serre functor is just a shift by d, by the Calabi-Yau dimension. And other comment, if, yeah, very important thing, if such a functor exists, so by this property here, by this defining equation, you can see it actually has to be unique up to natural isomorphism. It's kind of clear, right? Because this will, right, the right-hand side doesn't depend on S, but the left-hand side, this sort of gives a definition of S almost. But, you know, it might not, even if a triangulated category satisfies these finiteness condition on X, it might not have a Serre functor, but very often they do have Serre functors. And I'll give a general condition under which there is a Serre functor. Yes, and also, so example with the kind of where the name comes from, Serre functor. So if C is the bounded derived category of coherent sheaves on some smooth projective variety X, then just this equation, this isomorphism becomes Serre duality, where S is the functor of tensoring with the canonical sheaf and shifting by D. Sorry, so just plug this in, and then this equation just becomes the statement of Serre duality in that context. Okay, so this is what the Serre functor is. It just is tensoring and shifting by D. Yeah, so now the point is that, so this is actually many categories under sufficiently nice conditions have a Serre functor. The statement is that if C is the homotopy category of a DG category over some field, it should be proper and smooth. So these are kind of categorical analogs of the notions for varieties. But then under these conditions, there is a Serre functor, which has this form. It's given by, before I discuss this, maybe, yeah, what does proper and smooth mean? So proper means that there is a, first of all, there should be a generator of this category. Generator means, right, that if I start with this object and now I take sums and cones and shifts and direct summons, then I will eventually construct all objects of the category. And it's equivalent to C being the category of perfect complexes. Yeah, actually this over some DG algebra A. In fact, A is just endomorphisms of G. That's kind of the correspondence. Kind of, you need a endomorphisms in the DG sense, but since this is a DG category of G. I mean, it makes sense, right? So the statement, so having a generator is equivalent to being perfect on DG algebra, but more precisely, it will be the DG algebra will be just endomorphisms of that generator. And the other condition is, I guess, what we assumed previously, that this X finiteness, that the sum of dimension of X group between any two fixed objects is finite. And if you've written the category as perfect complexes over something, whoops, then you just need to check that A is has finite dimensional cohomology. So, and then if you know it for A by kind of long exact sequence arguments, you can get it for all other X groups. Okay, so that's what proper means, and it sort of corresponds to, there's some statements about this corresponding to properness of schemes. And then what is smoothness? Kind of slightly less intuitive. It means that, so by assume already that it's proper, or at least that C is perf of some, that you have a generator. I mean, it can also be defined if you don't have a generator, but I'll assume that for simplicity that C is perf of some GG algebra. And then smoothness means that A is in the category of perfect complexes. So A as a diagonal bimodule should be in the category of perfect complexes, should be a perfect bimodule rather, right? So modules over A opt tensor A are just bimodules. And perfect means that, so A opt tensor A is the free bimodule, and then I can sort of everything that has a resolution in terms of this free bimodule, and is a direct summand of some kind of cones will be perfect, right? So this means that the diagonal thing A can be written as some kind of direct summand of some iterated cone of A opt tensor A. Yeah, so that's smoothness, and particular nice if I proper and smooth. Then the Serre functor is given by tensoring with the dual of the diagonal bimodule. It's kind of abstract nonsense in the end, but right. So what does it mean? So A, again, I interpret here as the diagonal bimodule, and I take its dual as a kind of as a vector, as a K dual, so sort of the vector space dual, but that still has a bimodule structure. And tensoring with that bimodule induces an autoequivalence of the category, of the DG category. And the statement is that this is the Serre functor. Okay, I mean, you can just kind of remember that maybe that if it's proper and smooth DG category, then it has the Serre functor, right? Since it will be uniquely determined anyways. It's not so important how it's constructed, but if you're curious, this is how it will be defined. And then you can also see kind of where the conditions enter, the smoothness and properness, for this to make sense. Okay, any questions so far? Okay, so now that we know about Serre functors, there's kind of a little bit of a generalization of Calabi-Yau categories, which are called fractional Calabi-Yau. And so this means that some power, so Calabi-Yau again, it just means that the Serre functor is the shift by D, by the Calabi-Yau dimension. And for fractional Calabi-Yau, you weaken this a bit, you just require that some power of the Serre functor is a shift functor. And then if the cube power of S is shift by P, then by definition, the dimension will be P over Q. So this can now be a rational number as opposed to an integer. Yeah, by the way, the Calabi-Yau, it can very well be negative. So for any integer, you can have Calabi-Yau category of that dimension. Even though it doesn't come from geometry, the negative Calabi-Yau categories, but they do happen. But here we get even rational numbers.
I mean, what is there a kind of motivating example I should keep in mind for a negative dimensional Calabi-Yau?
I think if you take sort of ring of dual numbers and you just put this variable in some degree.
I see.
Then, I mean, then you can just say that
you by defining the gradings appropriately, you
yeah.
I
mean, the simplest way to say it, I think maybe just you can define a spherical object which is sort of lives in negative dimension, then just look at the category generated by that. That's essentially what I'm saying. Okay. I think that there are some also related to quivers, some things like that. But yeah, it doesn't. It's kind of a little bit esoteric, so we don't encounter them a lot. Yeah, but here, so for fractional Calabi-Yau, the first example, simplest example is if you start with a Dynkin quiver. So this means you have either A, D, or E type Dynkin diagram, and you put some orientation on the edges, and that turns it into a quiver. And then you look at the path algebra of that quiver and look at its bounded derived category of finite dimensional modules. Then that has fractional Calabi-Yau dimension 1 minus 2 over h, where h is the Coxeter number, which it has some kind of definition in terms of the root system or the representation theory of the corresponding group. I mean, you can sort of look up on a table what is it for each of AD and E, what is Coxeter number. Right, so in this case, some power of the Serre functor is a shift. And it's not very surprising that they have to be fractional Calabi-Yau, because these categories are all representation finite. So they have finite number of indecomposables up to shift. And so it's clear if you sort of have some action on a finite set, essentially, it has to be periodic, essentially.
Would it be hard
and so more.
Would it be hard to actually give the Serre functor there?
I'll talk about in the AN example. I mean, the Serre functor is defined what's called, I think, Ausländer-Reiten translation. I'll explain geometrically what it is in the AN case.
I think you can write it in terms of reflection functors, like the Coxeter element for reflection, more generally, which probably is what. Well, we'll see after you say the AN case. Yeah.
Yeah, I haven't kind of most familiar with the AN case. The other ones I didn't really sort of explicitly try to compute what the Serre functor does, but it's
sure.
Actually the D case you could also do in this geometric way. Yeah, let's just look at the AN case maybe. And so here I want to use the fact that the bounded derived category of this AN quiver. Yeah, and by the way, it's well known that the orientation of the arrows doesn't matter really. So these categories up here, this doesn't depend on the orientation of the arrows of Q. It just depends on the underlying Dynkin diagram. And that is proven using reflection functors, for example, as Tony mentioned. And this category has an interpretation as a Fukaya category of a disk, two-dimensional surface with boundary, which has n+1 marked points on the boundary. And yeah, if you don't know about the Fukaya category, then at least some kind of the first fact about this, the indecomposable objects up to shift in this category correspond to chords, so kind of curves connecting two different points on the boundary up to homotopy. And so if you know about the representation theory of these quivers, as I mentioned, there's finitely many, and it's kind of, you can very nicely visualize it in this Fukaya category picture, so that all these correspond to some chord. And then, there's some way to make sense of morphisms. They correspond to essentially chords meeting either at the intersection in the interior or intersection at the boundary point. And then kind of funny thing here that a triangle in the triangulated category, at least some of them actually look like triangles in this chord picture. If you have a triangle in the chord picture, you get a triangle in the triangulated category sense, though you don't get all of them. Yeah, and so what is the Serre functor? So there's the Fukaya category interpretation. What it shows is that there is kind of a symmetry, the cyclic symmetry, that wasn't apparent in the quiver description. Namely, there's some autoequivalence, which is clockwise rotation by sort of one click, moving from one marked point on the boundary to the next, so kind of a rotation by 2 pi over n+1. And because of the way grading, so you might expect that the n plus first power of t is the identity, but because of the way grading works in Fukaya categories, it will actually be the shift by -2, which means that, and in fact, S, the Serre functor does just this t, but composed with shift by 1, right? And then we see that the Serre functor, from that it follows that the n plus first power of the Serre functor is the shift by n-1, and therefore the fractional Calabi-Yau dimension of AN is this n-1 over n+1, which corresponds to this Coxeter number being n+1. Right? It's essentially this other, it's equal to 1 minus 2 over n+1.
Yeah, I think that T, I think that T is like a product of derived reflection functors corresponding to a Coxeter element in the symmetric group.
Mm-hmm.
So I think if you just take that, I think that gives the Serre functor and the other types. Just lift take the positive braid word for a Coxeter element.
Yeah, thanks for that.
Okay, yeah, okay.
Yeah, oh, actually, this could be extended to the D case as well, because I recently learned that it's the DN category. You can think of it somehow as a Fukaya category of a disk with an orbifold Z-mod 2 point in the interior. And it's DN is what's called skew gentle algebra. So this AN is an example of gentle algebra, very simple one, and then this orbifold stuff for skew gentle.
So that orbifold point is somewhere in the middle of the disk?
Yeah, somewhere. I mean,
okay, and then the positive roots of DN still have some interpretation as like the indecomposable objects still have some interpretation as chords in this picture.
Yeah,
or?
yeah.
Okay,
that's right. Yeah, I mean, and it's kind of, you can see right that the DN quiver is kind of like a Z-mod 2 quotient of the AN quiver.
Yeah.
Of the.
Yeah, with one orbifold point. Yeah.
Sorry, I think I cut out there for a second. Yeah, I was just saying that if you think of this A5 quiver, and then it has this Z-mod 2 action, just reflection. And if you take the orbit category of representations, then oops. Right, this gets identified with this gets identified with this, but then this guy is kind of a fixed point of that Z-mod 2 action, so it splits into two in the when you take kind of the orbit category. So then you get so D4 picture. Right, where now this point corresponds to both of these, which are split. This point, this. So it sort of comes from that, and so you can think of take the disk and take the Z-mod 2 quotient at this fixed point, then you're left with the disk with an orbital point. And then objects again have nice geometric interpretation. Okay, so yeah, we kind of saw that we can extend the notion of dimension from Calabi-Yau if we look at this Serre functor. And in particular, right, the fractional case was when the Serre functor is essentially periodic. The simplest dynamical behavior in a way. So the idea is maybe that in general, even though the Serre functor doesn't need to be periodic, maybe we can extract some kind of dimension by studying its dynamical behavior, meaning to look at very large powers of the Serre functor, sort of in the limit. And so one sort of, when you have a dynamical system, one of the first invariants you can look at is its entropy, which measures the dynamical increase of complexity, so kind of how complicated the dynamical systems, or how strong it's mixing in some sense. And in the context of triangulated categories, there was a paper a few years back with Dimitrov, Zarkov, and Kontsevich, where we called dynamical systems and categories, kind of generic title, where we define an entropy for an endofunctor of a triangulated category. And I think you might have heard something about that from Tony yesterday, but this will be then just kind of a review a bit. So if you have a triangulated category and assume it has a generator, maybe it's not completely essential assumption, but I mean, most of the examples we're interested in have a generator anyways. Then first of all, you can define the complexity of any object relative to this generator. And this will be actually not just a single number, but some real valued function, which takes into account the various shifts. And once, for understanding dimension, it will actually be important to not just look at to not ignore the shifts, but to actually consider this entire function. So this is a function delta sub t, and it's given by, so by definition, if G is a generator, then any object we can construct as a direct summand of, direct summand of some kind of iterated cone of copies of G shifted by some integers n sub I. So the fact that such a kind of tower exists for any object is the defining property of a generator. And now we can look at, you know, we want to kind of find the most economical way of generating E out of G, which means we take the infimum. So if you set T equal to 0, then this is just the number of copies of G you needed to construct E. But to sort of take the shift into account, you can add this power E to the NIT. And then you take infimum, to find sort of the optimal way. And this is this complexity. And then you define the entropy of an endofunctor. All my functors are exact, kind of preserved triangulated structure. I don't really care. I think it's very unusual to look at functors which are not preserving exact structure and so on. But and then the entropy is again, it's a function from real numbers to, could be minus infinity in some degenerate cases, but basically real valued function of real line. And it's given by measuring the exponential growth rate of this complexity. So this generator G, and now we look at what happens to this generator if we apply f to it, this functor, many, many times. And complexity will typically grow exponentially. So it could, I mean, grow less than exponentially, but in fact, it grows at most exponentially. And what this 1 over n log is doing is it's measuring the exponential growth rate of this complexity. And again, the whole thing can depend on t, or you could just look at t equals 0. That would, and then that would ignore the shifts. And what we proved, one of the first important things is that this is, even though this complexity depends on G, then this entropy, once you go to the limit, doesn't depend on the choice of generator. There's some kind of argument like that. If you have another generator, then you can compare that there's some kind of universal bound of the complexity of one or the other. Okay. So this maybe looks a little bit difficult to compute. Right here, you need to take some infimum over some huge set, but at least in the case when C is a nice example, it's the homotopy category of a smooth and proper DG category, then there's a much simpler way to define, to compute this entropy, namely where instead of this complexity, which looks at all possible ways of expressing E in terms of G, you just look at the dimension of the X group from G to F applied n times to G. And here again, generator is irrelevant. Okay, but this is in the smooth and proper case, and so unfortunately it doesn't. I think if you would define it like this, it's not clear if the category is not smooth and proper, but then it's not clear that it's independent of G if you were to use this as a definition. Just kind of some remark that this is a sensible notion if it sort of corresponds to, because there's already existing notions of entropy in dynamical systems, which are not categorical, but kind of more geometric. So for example, if you have F is a regular self-map of some smooth projective variety, then it deduces some functor on the bounded derived category and the entropy of that. And here I'm taking the value at 0, ignoring shifts. I think in these examples, actually, it's just constant, so it doesn't really matter. But you just take the value at 0 is then the kind of classical entropy of this regular map, which in fact can be computed as just some spectral radius of some induced map on cohomology. And then another example related to the Fukaya category. If you take Fukaya category of a surface and take a pseudo-anosov diffeomorphism, then that also has some entropy, which is some kind of, if you know about pseudo-anosov diffeomorphism, they stretch in one direction, shrink in the other. So there's some kind of stretch factor here, and that this stretch factor is the classical entropy of the pseudo-anosov, and also it's the entropy of the seduced autoequivalence of the Fukaya category. And here this is, in some sense, slightly more interesting because it's not just a spectral radius, at least not on the cohomology of the surface. If you pass to some double cover, and then
in these Fukaya category examples, is it I mean, like if you have a pseudo-anosov, then there are these transverse measured foliations that are the that correspond to the pseudo-anosov diffeomorphism, the ones that are just where the measure is just scaled.
Yeah, two invariant. Up to
So
scaling.
do those foliations acquire any categorical meaning in the Fukaya category? Or in something related to the Fukaya category, do you know?
That's a good question.
I mean, you want to say that it's something like eigenobjects of this end of this F, but they probably don't live in the Fukaya category, but maybe they live somewhere sensible. I don't know.
Yeah, they should do some kind of function, right? Some kind of real valued function on objects, I imagine. But I mean, there's this other connection. If you have a quadratic differential, which is kind of the two foliations together, then it gives something on, but it's a different Fukaya category, the Z-graded. So here, this is just a Z-mod 2 graded category.
I see, and the other one is Z-graded.
Yeah, so here, this is Z-mod 2 graded. There's no stability conditions. Yeah, it's an interesting question as kind of, can you characterize somehow these measured foliations categorically? But I don't know the answer to that. In fact, what's used here is that pseudo-anosov. So to prove this, you just look at this what's called geometric intersection number. If you have a curve and another curve on the surface, you look at, you know, when you isotope them so that they intersect minimally, then you can relate that to dimension of X group, the number of intersection points. So this at least this proof that these two entropies agree doesn't use the measured foliation. Okay, but yeah, what the main thing I wanted to talk about is to apply this notion of entropy to the Serre functor. And actually, I looked at that back when we wrote this paper. There were a couple of examples in this direction. And so first example, yeah, and again, the motivation is to kind of that we expect this to correspond to some sort of notion of dimension. And actually here there's some kind of good, or at least, yeah, this doesn't contradict that, that hope. So first of all, if X is a smooth projective variety, then the entropy of the Serre functor will be just a linear function, slope dimension of X. Right, so here it's important that we actually consider it as a function of t, not just the value at t equal to 0, which would be just 0, which is boring. But here it is this linear function. Oops, always doing erase instead of highlighting. And this comes from, if you remember what the Serre functor was, in these cases, it's just tensoring with the canonical bundle and then shifting by d. And basically what this comes down to is showing that this the shift by d sort of dominates the entropy, right? This is, if you just have the shift by d, then that would be its entropy. And then you also have this tensoring by the canonical bundle, and you just show that that only increases the complexity polynomially and not exponentially, so it doesn't affect the result. Then, yeah, kind of fairly obvious thing, if you have a fractional Calabi-Yau category of dimension p over q, then the entropy of the Serre functor is again line through 0 with slope p over q. It's fairly easy to show, just because Serre functor, some power of it is the shift. And then some, and also this explains, right, what it is in whenever q is a Dinkin-quiver, as I mentioned, then it's always fractional Calabi-Yau. So kind of natural question is, what if the q is not a Dinkin-quiver? So it turns out that if it's extended Dynkin, it's kind of Dynkin diagram where you add one node, create some affine root system, and then the entropy is just T. So it kind of has dimension 1, which is also sort of sensible because these categories are tame representation type, which means they have one parameter family of indecomposables. In that sense, they're also one-dimensional. And then if it's not Dynkin or extended Dynkin, it's Wald representation type. And in that case, an interesting phenomenon that actually in all the previous examples we had a line through 0. And here for the first time, you get that the entropy at 0, so if you set T equal to 0, you actually get something positive. So it will be of the form some positive number plus T. So it's still sort of dimension 1 in some sense, which it's also maybe not that unreasonable because they are these algebras, path algebras of Quivers are homological dimension 1. But here the Serre functor has some actual entropy at T equal to 0.
Where are these examples worked out? Is this in your guys' first paper?
Yeah, it's in this DHKK paper.
How on earth do you prove number 4? Like, it's a very cool statement. Somehow I didn't remember that.
Yeah, it turns out it's just a spectral radius because it's almost preserving the T structure. Not exactly, but and once you know that, I think, and then in these cases definitely it's just the spectral radius. So I don't remember.
Okay.
It wasn't that bad actually.
But you can already see this feature at the level of like looking at what happens on the growth group.
Yeah. Okay. But then you might, so here it's always a line, and the slope it's sort of some reasonable notion of dimension. But of course, in general, this entropy of the Serre functor doesn't need to be a linear function. Actually, I don't know kind of in general what you sort of expect it to look like. Definitely it can be like piecewise linear, things like this. But what you can do is kind of look at slope at sort of very large values. So this is what now a more recent paper from 2 years ago or something by Elagen and Luntz, which is titled a very nice paper, 3 notions of dimension for triangulated categories. And actually Serre dimension is just one of them. The other that they look at are Rouquier dimension and diagonal dimension. So these are sort of more inspired by homological algebra, and there are always integers, non-negative integers. And they sort of see what is known about them, what is not known, and compare them. So I'll say that there's there's a lot of open questions. This is mostly about sort of many open questions in this about the dimension of triangulated categories. So what's the definition they give? They talk about upper Serre dimension and lower Serre dimension, and often they're, in fact, in many cases they're the same. And always in these cases where the entropy is just a line, they are the same and they are the slope of this line. So what you do is you look at, again, kind of dynamical thing. You look at x from G to the Serre functor applied many times to that generator, and you look at the upper Serre dimension. Yeah, it's kind of, there's a confusing thing about grading. The shift by n is shifting down by n, so there's some kind of signs and stuff. If I wrote everything correctly, it should be that the shift by n, if the Serre functor is shift by d, then Serre dimension should be d. If it's minus d, then I got some sign wrong somewhere. But so you look at the smallest I, which is the lowest degree of non-trivial X group, and then take this limit 1 over n as you then apply Serre functor many times. And there's kind of sort of the opposite way. There's this lower Serre dimension. And here C is some triangulated category with Serre functor. In fact, they mostly care about the case when it's, again, this smooth and proper. But this makes sense for any triangulated category with Serre functor, and X groups being finite enough, and having some generator G. So in the relation to entropy, I already mentioned it. So this is if you take the entropy as a function on the real line and you look at sort of the linear growth as you send t to plus or minus infinity. The upper Serre dimension, yeah, here I need C to be smooth and proper. I mean, I think basically because, right, this definition is in terms of X groups, whereas entropy is in general defined in terms of this complexity to relate the two. That works well in the smooth and proper setting. And then the upper Serre dimension, yes, so this limit, here you don't need lim in for lim sup or anything, just limit of this entropy, so the slope at infinity. Well, it's not, yeah, maybe it's not slope at infinity, but it's like linear growth rate of that function. And here t goes to plus infinity, and then for lower Serre dimension, you send t to minus infinity. Yes, so it's clear from that if ht, the entropy is just a linear function, then both the upper and lower Serre dimension will be just the slope. So in all these examples I gave before, you already know then what this Serre dimension is. And there's a slight variation on this. So Kutsevich suggests to not look just at these kind of uppermost and lowermost numbers, but at an entire set of real numbers where you take, so for each I you get, or rather for each n, you get this set of sort of degrees of non-zero X groups from G to S applied n times to G, and kind of normalized by dividing by n. So you get some set of real numbers for each I, and you look at the limit of these sets of real numbers, which I think it means essentially, right, look at any possible sequence. You have a bunch of sets of real numbers, and so pick any one of the numbers in each of these sets. You get some sequence, and if it converges, then it belongs to the limit set. Okay, but I mean, I don't know if how complicated these sets can get. No idea. Maybe it's just always sort of an interval, or I mean, in many cases, anyways, it's just a single point, and then these upper and lower Serre dimensions are the same. Yeah, and also instead of looking at X from some generator, you can instead look at X in the category of bimodules or functors from the identity functor to S shifted by n. Then that will be in the smooth and proper setting. That's equivalent to looking to picking a generator and looking at this X inside the DG category.
Do you know, have you, or do you know if anyone has looked at what these sets are for other functors other than the Serre functor? Like for some simple pseudo-Anosov autoequivalences or anything like that? I mean, this.
I mean, for pseudo-Anosov, if it's in the Z mod 2 graded setting, you basically just get a number always. You can't really.
No, but in the Z graded set, I mean, you could take like a pseudo-Anosov braid in the 3-strand braid group.
Oh yeah, yeah, sure.
And
yeah.
I don't know. It looks it looks like maybe you could get some Cantor set like things or something. I don't know.
Yeah, I mean that would be yeah. Actually, I don't know if any computations of the set.
Great. Okay.
It's not the point. Or I think this is wide open. You can. Okay,
students here. We should try to compute. We should try. I mean, we should try to compute this set for sigma 1, sigma 2 inverse.
Yeah.
Next week. This is a cool idea. This set. Yeah.
I think in many cases it might just be kind of a single point or an interval. It would be boring, but maybe it will be something like Cantor set. Yeah, that would be cool. Okay, but you know, since they talk about this upper and lower Serre dimension mainly in their paper, I'll stick to that. I don't know much about this set. So some of the stuff which they prove is, I mean, this also already follows from kind of what I said so far, that X is a smooth projective variety. Then the upper and lower Serre dimension agree and are the dimension of X. Same in the fractional Calabi-Yau case. Then you have this nice additivity property. You take a tensor product of DG categories, take the appropriate triangulated completion. Yeah, and they should be probably smooth and maybe they don't need to be smooth. Yeah, I think probably it just works for any categories with Serre functor. That it's additive undertaking tensor product. And so one thing which is kind of weird, where it doesn't behave like you would expect a dimension to behave, there are examples where you have a semi-orthogonal decomposition. So essentially it means, kind of, if you think about it in terms of PG algebras, it means that C is kind of block upper triangular with some block A and B extension of the two by some bimodule. There are examples where the semi-orthogonal summand has bigger upper and lower Serre dimension than the entire thing. And in fact, they come from sort of quiver examples, with some quiver relations. It probably happens a lot. Yeah, actually, Kontsevich in sort of his talks on this stuff argued that for nice semi-orthogonal decompositions, which come from somehow from the spectrum of some quantum operator, and C is bounded drive category, then this should not happen. So maybe there's some class of sort of nice semi-orthogonal decompositions which have some geometric meaning where this doesn't happen, and this is some kind of artifact of the purely algebraic world. And then you also prove some kind of semi-continuity. If you have a family of categories over, say, some polynomial ring or something, then they prove some kind of semi-continuity statement. I don't want to get into detail. Yeah, but the main point is that kind of there's much more that is not known about this Serre dimension and its relation to other notions of dimension than is known. And these are also questions which are taken from their paper. The first three. So for example, is it possible that the Serre dimension is an irrational number? There is not any known example. Is it, yeah, and what are, for example, can you classify categories just with Serre dimension 0? That seems like should be fairly straightforward to classify things of dimension 0, but this is also not clear. Yeah, and in all these cases, sometimes the assumption is that C is, smooth and proper. It's nice enough. So then the relation, which is sort of one of the main themes of their paper, they also look at this Rouquier dimension and the diagonal dimension, and what's the relation to them. So in some cases you can prove some inequalities, but in general, there's only conjectured inequalities. So they have some more detailed conjectures on this, how they are related. So of course, they're not always the same. I mean, these are integers that can't be in general, but you expect some kind of bounds to exist. Yeah, and then Kontsevich, so recently he gave some talks, and this stuff is not only available in sort of YouTube videos, as far as I know, and lecture notes. But he has some program to connect. So this is some ingredient in some understanding of birational geometry in terms of semi-orthogonal decompositions. And so he has some conjectures about this Serre dimension when the C is some semi-orthogonal, part of a semi-orthogonal decomposition in the bounded drive category of X. And this semi-orthogonal decomposition somehow comes from quantum cohomology. And then there he has some relation, somehow some way to compute the Serre dimension in terms of some growth of some solutions to some ODE. Actually, I don't understand all the details, but it looks very interesting. Yeah, and maybe just to mention, so this Rouquier dimension is basically you look again, it's kind of very hard to compute actually. And it says that there should be some generator. You look at for all possible generators of the category, you look at the one which generates the category the fastest, where fast means, how many cones do you need to generate any other object, and direct sums and summands and shifts are free. So they sort of don't take time, but every time you take a non-trivial cone, you take some time one, and then the fastest generator is the Rouquier dimension. And it's kind of, you can imagine it's sort of hard to compute because some statement about all possible generators of the category. Whereas for Serre dimension, I just need one generator to look at these iterates under the Serre functor. And then diagonal dimension is something about resolving the diagonal bimodule in terms of the free one and how many, again, what's the generation time of the diagonal essentially. Okay, but I think that's all I want to say. So thanks for listening.
Please join me in thanking Fabian. All right. Any questions from the audience?
I have a question. Sort of a vague question, but do any of these invariants, these notions of dimension, have they been used as invariants to prove something else, to you know, distinguish categories, or to learn something else about categories, or as invariants?
Question, yeah. I mean, I guess there's so many invariants of TG categories that it's almost, you know, maybe, but yeah, I kind of find it more like intrinsically, it's an interesting question for me. So.
Sure, it is. I was just curious.
I don't know of an application, but I mean, this program by Kontsevich, I think potentially needs some application of this notion of
birational geometry.
In birational geometry, yes. And you know, you need to look at these talks for more details. I can't tell you about those. Yeah, I think right now it's mostly kind of intrinsic and studied for its own sake.
Yep. Tony?
What's definitely good about it is because it's easier to compute. The problem is if you have an invariant, but it's sort of very hard to compute, like this Rouquet dimension, then it's not the most useful invariant, but at least the Serre dimension is I think something which you can hope to compute much more easily.
What paper was it that discussed that you mentioned that discusses this Rouquet dimension, diagonal dimension, and Serre dimension?
It's just Lagenlunds.
Lagenlunds, okay.
It's called three notions of dimension for triangulated categories. I think from 2019.
Yeah,
maybe if you can put it on this website.
Yeah. I'll put. I think it's already on the website. I think.
Okay.
But, yeah. Yep. Any other questions from the audience? Right. If not, then let's join me in thanking Fabian again. And thank you so much for